Quantum mechanics is the subject that we're going to talk about today. I'm going to leave you to read number 1 and number 2 and head down to point number 3. The quantum mechanical model is the last in a series model that helps us to explain the physical ways that an atom looks and how it behaves. The quantum mechanical model is based on quantum mechanics. And let's talk about the word quantum. Quantum means a piece of, and that in terms of the quantum mechanical model in our dealings with the atoms has to do with the fact that energy can only come in discrete bundles. If you were to think of this as a set of stairs, you could have this as an amount of energy, and this is 2 times that amount of energy, and this is 3 times that amount of energy. You cannot have any energy that is not a multiple of this, the lowest energy. You cannot have a half or 1.725. That is what is known as a quantum. If you were to look at energy along a pathway like this, there could be an energy value anywhere along that portion of rise. Okay. We're going to talk about electrons and light together because they share a couple of things. Number 1, that you probably know, light behaves in 2 ways. It can behave as a wave, and it can behave as matter. The electron can do the same thing. Light belongs to the electromagnetic radiation spectrum, and we're going to study light waves and light particles in order to understand the electrons, and we will talk about that in a little while. Let's do a really quick refresher on a wave, and I will leave you to read what a wavelength and the frequency are. The only thing I need to tell you about velocity is, which is speed in a direction. All electromagnetic radiation moves through a vacuum at the same velocity, which is the speed of light, 3.0 times 10 to the 8th meters per second. We can calculate, knowing that this is defined quantity, we can calculate the wavelength and the frequency, knowing the speed of light. Please note, in some texts, instead of the Greek letter nu, that they use the term F for frequency. This is what you use in college, so we're going to use that. You can see that wavelength and frequency are inversely proportional. The longer the wavelength, the shorter the frequency. Okay, so here we have the entire electromagnetic spectrum. Push that and stop. And let me pull this down. All right. A quantum, we have already explained. A photon is a certain type of quantum of light. It is a packet of light that is emitted or absorbed as electromagnetic radiation, and it also has that characteristic that it has a certain energy associated with it, depending on its value. So you can only have a multiple of the energy that is emitted or absorbed. Okay, now a little background on this. We know, according to the Bohr model, that if we have the nucleus here, the electrons are in, as we discussed, in orbits in defined spaces around the nucleus. If we have an electron in the lowest energy shell, we must add energy in order for it to go to the next highest energy level. This would be moving from here to here. You cannot move this electron part way between a shell. It has to make the jump, the quantum leap, between one shell to another shell. This is energy needed to be absorbed in order to make this jump. When it does make this jump, it is unstable and it will fall down to its starting position, the ground state, and when it does so, it will release a photon of light of a particular energy that is equal to the amount of energy that needed to raise it up an energy level. So if it takes X energy to move it up, X energy will be released when it comes down. Planck described a way to quantize this energy, and he said the change in energy from one level to another level is described as by the Planck's constant, which is this very small number, times the lowest frequency that can be absorbed or emitted. So if we are starting with this, and would then be equal to 1, so the energy needed to raise it up to the second energy level depends on its frequency times Planck's constant. And then the energy lost, as perhaps this goes to this, can also be quantized using this. I'm going to tell you that right now this is in the equation only for you to recall that the energy, the change in energy, must be in a multiple. So for the most part, your equation is going to look like this. So now we're going to move down into a little more about light, so we can measure the amount of energy that was released when a electron went from higher energy to a lower energy level, and that will tell us the amount of energy that was needed to promote it to the higher energy level in the first place. A continuous spectrum is white light. It is all of the colors of the rainbow orangey band. It is made up of all of its component wavelengths: red, orange, yellow, green, blue, indigo, and violet. Okay, so moving on, let's look at a hydrogen atom. And when a hydrogen electron is in its lowest energy level, it is called the ground state. And when you add energy to it, it can go to any one of the 7 outer energy shells. And remember, these N is equal to the principal quantum number, and that is a shell, or another term for that is an energy level. So let's say you add a whole bunch of energy. You can promote that electron all the way up to the 7th energy level, and then it will fall back down to its ground state where it is most stable. So here's another way to look at it. Here is your electron. It starts out at the ground state. You can excite it, adding energy, and remember you can use energy in a variety of different forms. If this electron fell to the 2nd energy level, it would emit a photon of light that is equal to the amount of energy it would take to promote it, not from 1 to 3, but from 2 to 3. It would then fall down to the ground state at some point. Okay, this was hard for me to format. So the equation for the energy phase when an electron moves from one level, that's where it started from, to another level, is this. So I would like you to put these big brackets around there because it was too hard for me. So you take the final energy level and square it, take the inverse of it, subtract the initial energy level squared, take the inverse of it, and then multiply it by this number, make sure you have the negative, and that will tell you the amount of energy emitted by an electron when it goes to its lower energy level. Let's do some math here. It says calculate the energy required to excite the hydrogen electron from n equal 1 to n equal 2, and calculate the wavelength of light that must be absorbed by the atom in its ground state to reach this excited state. Well, we know that E is equal to this constant. Oops, almost forgot the negative. And then we would take the inverse of the final energy level, that would be 2, quantity squared, minus the inverse of the initial, which is 1 squared. And I do some math. I always clear these first. So 1 divided by 4, 1 divided by 1, this minus this times that is 1.633 times 10 to the negative 18 joules, a very little amount of energy. We notice this is a positive number. That means energy must be absorbed into the electron to promote it from a lower energy level to a higher energy level. And then it says, calculate the wavelength of light that must be absorbed in order for this to happen. So let us recall that we know that the speed of light is related to the wavelength and to the frequency, and we also know that energy is also related to the frequency. If I put this in here, I can solve for that, and so that would be some algebra here, and this is the equation. So the wavelength would be equal to Planck's constant, 6.626 times 10 to the negative 34, times the speed of light, 3.00 times 10 to the 8 meters per second, divided by the energy that I've calculated that is necessary, 1.633 times 10 to the negative 18 joules, and that will give me this wavelength in meters. Here is a warning to you. You are using the speed of light, which is calculated in meters per second. Very commonly, the wavelength of visible light is given in nanometers. You must, if you are using 3.00 times 10 to the 8 meters per second, have your wavelength in meters as well. What is the conversion factor? 1 meter is equivalent to 1 times 10 to the 9th nanometers. Nanometers very small. Okay. The blue color in fireworks is often achieved by heating copper 1 chloride to about 1200 degrees C. Then the compound emits blue light having a wavelength of 450 nanometers. What is the increment in energy, the quantum of energy, that is emitted at 450 nanometers, or 4.5 times 10 to the second nanometers by copper 1 chloride? Okay, so if we know this, and we know that the speed of light, then we know that we also can figure this out. In order to figure out the energy, we need to know the frequency, and they have given us the wavelength, so this is a two-step problem. So the frequency is equal to the speed of light over the wavelength. We're going to match our units here, so I know that 450 nanometers is 4.5 times 10 to the negative 7th meters. You can do dimensional analysis on your own. So 3.00 times 10 to the 8 meters per second over 4.50 times 10 to the negative 7th meters will give me a frequency have 6.67 times 10 to the 14th hertz, which is also seconds to the negative 1. That means that the energy involved here is equal to Planck's constant, times the frequency, and then equals the sleep rate. Okay, here's the thought process for you. N2 molecules absorb ultraviolet light, which is of higher energy than visible light. I2 molecules absorb visible and ultraviolet light. Which of the following statements explains the observation? More energy is required to make the N2 molecules vibrate than is needed to make the I2 molecules vibrate. I think that answers the question here. Oops, I have a circle of doom here. So it's a false statement. More energy is required to remove an electron from the I2 molecule than removed from the N2 molecule. Also doesn't answer the question. Visible light does not produce transitions between electronic energy levels. That would be a shell in the N2 molecule, but does produce transitions in the I2 molecule. That does. And the molecular mass of, that answers the question, the molecular mass of I2 is greater than that of N2. That is true, but also does not answer the question.